So first I wanted to point you, well, there is not a lot of website, but there is like a little bit of a website. Somebody was asking me about the course syllabus, so that's what I really quickly put there. Probably the most important thing on this site are the links. So there is a link to my website. That's not the most important one. There is the link to the YouTube channel where I'm putting all these recorded videos. So as I speak, it's being recorded. And most importantly, so the Piazza thing is what we use for announcements. So I hope that everybody noticed that I posted there the MATLAB license for you guys, for students taking courses like this one is now available. And just like half an hour ago, I posted on Canvas. So I think if you just go to Canvas and put you should have this working. I hope by now. Some people had some like issues, so notice that there needs to be the UPenn thing. If you have there like Wharton or something, that might not work. And this is our course. And I just posted there a new assignment to give you some fun things to try with MATLAB. Now you actually have a MATLAB. I mean, even if you didn't download your own copy, you can always use it in the labs, right? So it's just nicer to have it on your laptop. And here is the first homework. So you should just look at it. It's due next Friday. It's this PDF thing. And those are just some very, very, very simple things you can try in MATLAB. So whenever you get a chance, read through it. Then there will be some, the DAs will hold office hours and recitations next week. We'll still need to schedule one of the times for the office hours, but those will be the right places if you want some hands-on help. If you just want some offline help, then go to Piazza, just post there something. And if you want to talk to the TAs or myself, then the office hours and the recitations are the right spot to do that. All right. Okay, so let's get down to business, shall we? So the last time I was talking about vector spaces, and I was trying to make the case, actually, so that's again like a really brief recap. Vector spaces, that's what we talked about last time. I was trying to make the point that it's not boring, but I might take it back, it actually is pretty boring. So if you want to remember just like one thing about vector spaces, remember that it's a set which is endowed with some operations which make it an algebraic structure, an algebra. And in this special case, it's called the vector space. And the operations we give it is the addition of vectors, the plus, and the multiplication by scalar. And these operations, they have to observe a number of properties. It was the 10 properties that was boring you to death the last time, like the commutativity on addition and associativity, blah, blah, blah. There's a lot of them, which makes it boring. The point is that this creates an algebraic structure we can do interesting things with. I guess even better point is that this is something very smart people thought about very carefully, and they came up with some very cool observations, and that's basically what linear algebra is about. Okay, so this was the definition of a vector space. So remember just this. It's a set with some operations, and the operations have some very interesting, very special properties, which are not for granted at all. The next thing we talked about was linear transformations. So if I have a linear transformation T from one vector space V1 to another vector space V sub 2, then the transformation is called linear if it's true this. So you should now be ready to be able to like parse it like a compiler to like understand what types are these. So the x and y are vectors, and the x and y are vectors in the vector space V1. So I could also write x, y are from V1, and I should write like for each x, y from V1. And alpha, beta are scalars. So we are working with vector spaces over the field of real numbers. Yeah. Tx and ty are also vectors, and they are from the vector space V2. So tx is from V2, ty is also from V2. And this is again a linear combination in the vector space V2. And one of the properties of, or some of the properties of vector space is guarantee that if I multiply by scalar and add them together, I also get something that's in the vector space V2, right? But this property is the linearity property, the key thing of a linear transformation. And then what we discussed in detail the last time, this bar thing, right? Yeah. Is that the linear transformation is completely characterized by its action on basis vectors. The simplest set of basis vectors for the R to n-dimensional real vector space is this E1, E2, En vectors, right? Let me give them like little arrows to make it very clear that these are vectors. I guess I could like also write like arrows here. Arrows are sometimes used to like basically highlight the fact these are vectors, to differentiate it from scalars. So do you remember what is the E1? So if I have n dimensions, that means there is 1, 1, and there is n minus 1 zeros. That's what is E1, right? And the action of the linear transformation is completely captured by the action on the basis vector. So all I need to know is TE1 and so on to TEN. TE1, TE2, and so on up to TEN. So those are again some vectors. This time they would be vectors from the V2 vector space, from the vector space it maps to. The V2 doesn't have to be different from V1, but it can be the same vector space. That's quite often the case. But in general, they can be different. That's the point here. And so these guys are also vectors. So also some like column vectors. So what I can do, and I think that's what we ended with, is that I can put them all together in one table of numbers. And that's nothing but a matrix, right? So this is like one column here, will be like another column, and so on. And the last column would be TEN. So this gives me a matrix. In general, it can be rectangular if the dimension of V2 is different from the dimension of V1. If the dimensions of both of them are the same, then the matrix could be a square matrix. And I guess, so why is this? So maybe I can like write it. So if I take an arbitrary vector V from the vector space V1, then I know that I can write it as a linear combination of the basis vectors, right? So this type of sum. So, and the action of the transformation on V due to linearity is just this. So the action on the standard basis vectors and taking the same linear combination. So because this would be sort of tedious to always like write these things, or I could also write it. This is equivalent to writing it with a sum, right? As you know, of course, alpha I T E I. But it's still a little bit a tedious thing to write. So we define matrix vector multiplication. So this is going to be a matrix. I can call it, for example, the matrix M. And I can say that this is a matrix vector product, where the vector is vector of alpha 1, alpha 2, and so on to alpha n. Which brings me to the new stuff. That's what we are going to start with today, and that's matrix vector multiplication. Here comes the first slide. So matrix vector multiplication is basically a way to succinctly, to nicely, elegantly describe the action of a linear transformation on a vector, right? So you remember by now that a matrix is just a representation of a linear transformation with respect to some bases, typically the standard bases, but could be different bases. And the action of the linear transformation is described by the action on the standard basis vectors. If I put them to a matrix, I can write the action as a matrix vector multiplication. So how exactly is it defined? It should be pretty much obvious from what I said before. So, but let's look at it carefully. So A is generally a rectangular matrix, so meaning m rows and n columns. Yeah, if you are not familiar with this notation, the first one is always the number of rows, and the second is always number of columns. So m rows and n columns. Oh, it's actually written here too. So there is like an operation here, which is like denoted with nothing, right? That should not surprise you because we often denote multiplication with nothing. It's just like this implicit operation there. And in this case, it means matrix vector product. So if I wanted to like draw it graphically, so let's say I have more columns than rows. In this case, my matrix is sort of like a rectangle of numbers, right? And the rectangle of numbers, this is, it starts with A11, that's like the first number. Then there is A12, and so on, and goes up to A1n. And it's really small, right? Let me draw a bit better picture. I'll draw it here. Does it work? Yeah. So A11, A12, and so on up to A1, and A13, of course. Here would be A21, A22 to A2n. Again, it would be A31, and so on. So it goes up to AM1, because m is the number of rows, AM2, and goes all the way to AMN. So I put these dots here. So this is what is in my matrix A. So all these A11, Aij things in general, so those are just scalars, right? And if the matrix originated from some linear transformation, then these columns here, so these are the columns of the matrix, right? The other way I could also look at the rows of the matrix. So these columns, they originated as transformation of the standard basis vector by the linear transformation, if I was looking at it this way. Now the vector v, I can write also as a column. So the v would have some coordinates v1, v2, and so on to vn. And this operation here is the matrix vector multiplication. I think we usually like don't denote it with any dot or something, so it doesn't confuse with the dot product, which is like a different operation, even though very, very, very closely related. So like this is like usually like nothing in between there. Actually, I should have written this longer, right? Because the point is that the length of this vector has to match with the number of columns, right? The n here is the same as the n here. So if I have, like, for example, 2 by 50 matrix, so I would have just 2 rows and 50 columns. I need to have a 50-dimensional vector to multiply it with. Otherwise, not defined. And it gives me back a vector which is now this dimension, size m. And it's vector of w1, w2, and so on up to wm. And this formula tells you how to compute the values of the coordinates of the w vector when you know the values in the matrix and in the vector we are multiplying it with. So what is it? It's just the sum. So if I'm looking at coordinate number I, so let's say on the first one. So I is 1. So I'm summing A11 times V1, A12 times V2, and so on up to A1n times Vn. Right? That's what this formula is saying for W1. Right? So the way you can look at it graphically, and I sort of like this, you can like look that you take this thing as maybe I can even do like little animations. Right? I can take this, I turn it here, and I put it there, and I essentially do a dot product of this row vector with this column vector. So I could also say that W1 is, so if my first row was R1, I can say that W1 is R1 dot product V. Right? I could say the same thing for the others. It's the same story. For W2, the only difference is that I take the second row. So my W2 would be, if this is my row number 2, I'm taking row number 2 and I'm doing dot product with V. And guess what? The same goes for all the other coordinates. So Wn is just the dot product of Rn dot V, right? And you know that we can write out the dot product by the definition of dot product and write out by coordinates, and this is equivalent to exactly this formula. So that's one way you can think about the matrix vector multiplication. So that's like the row picture. So maybe this is actually very good to build intuition about early on. So that, like, remembering this formula is like painful. Like you could memorize it, right? So you would try memorizing sum over j, aij times vj. It's very easy to like get it wrong and like switch the indices or something. But having like the picture that you like take the vector and multiply every row with it, that's something you will remember forever probably. So the column, oh look, I can also do this. So the column viewpoint is that I can be looking at the matrix two ways, either as a set of row vectors or a set of column vectors, right? So what I was doing here, I was like saying that the matrix essentially is if I have first row vector, second row vector, and so on up to mth. Ooh, look, I made a mistake here, right? This should be m, and this should be also m, and this should be m, right? Let's get this right. That's probably like the only thing that can go wrong in linear algebra. It was m rows and n columns. So if I have an m times n matrix, it needs to accept an n vector and returns an m-dimensional vector. Otherwise, it just would not match. Otherwise, it's not defined, these operations. So if I'm looking at a matrix as a collection of row vectors, so in this case, the R, just like here, the R1 is the vector of the entire row, right? So this point, the point of view of the multiplication is exactly as I wrote here, as doing, I do the lock. It's doing the individual dot products of V with R1, R2, and Rm, right? That's what I said here. I can also be looking at A as a collection of column vectors. So C1, C2, and so on. Let's not get it wrong. What's gonna be there? N or M? And obviously, right. I'll get you to think about it. If I have to think about it, you also have to think about it. So in this point of view, if I am doing the matrix multiplication A times V, so what it basically means is, so I can also give it like little arrows to highlight the fact that these are vectors. So in this point of view, the AV essentially means taking a sum over all the columns and doing a scalar multiplication like this. So what I'm taking the column number I, so I could also write it like V1 C1 plus Vn Cn, right? So I'm taking the column and multiplying it by the coordinate of V. So I guess I could say that A, so this is my A. My V is again V1, V2 to Vn, right? So that's like a long vector. And again, you can look at it as I like take this vector, rotate it here, and like hit every single column with every single coordinate or component of that vector and sum them all together. So it's like sort of like dot product, right? But applied on vectors, right? This is what it is. It's really just a scalar product of every single column and then summed all together. It's the same thing as doing the dot product individually. It's like different ways to look at it. These will be important when we're like doing the subspaces, the four fundamental spaces. This is something you should remember. And it's obvious that these two things are equivalent, right? Okay, is that clear? Good. So the one cool thing about linear transformations is that if you take several linear transformations and compose them, then you get again linear transformation. So first, what does it mean composing? That's like this composing functions. It means nothing special. It just means that first you do one, and then on the result you apply another one, right? So let's look at it a little more carefully. So now I have like 3 vector spaces, v1, v2, and v3. They could also be one and the same, right? They could all be Rn, right? If that's the case in a matrix, then that's a special case of square matrices, right? Because I don't have to deal with the m by n, but I have just like m by m matrix. So let's say I have 2 linear transformations. One goes from v2 to v3, that's f, and g that goes from v1 to v2. Then the composition means that I first apply g and then f. So g, let's see. G goes from v1 to v2. So after I apply g, I'm in v2. And then f takes v2 and goes to v3, right? So the composed transformation, the v, this is like the symbol for composition of functions, is a transformation from v1 to v3. That's obvious, right? What is I guess also obvious, but what I want to show here is that's also a linear transformation. And that's you just need to like look at the definition of linear transformation, right? So again, this is just a composition of functions. So it means first apply g, and then apply f on the result, right? So we know, so if we apply to alpha v plus b beta w, and we know that because g is linear, I can do this, right? It doesn't matter if I'm applying the g on the linear combination or if I do the linear combination after I've applied g individually on v and w. That's what the first, or I guess second equation, this one is saying, right? And then I can do the same thing because f is also a linear transformation, right? Well, because it's a linear transformation, then I can apply the same reasoning and get this. Which means that the composition, the f composed with g, is a linear transformation. Now, don't ask me why the convention works like this, that first I apply the one that's on the right, and so this is the first, and this is the second. I would think like that, at least for cultures that are like used to like reading from left to right, as we are, it would be more natural to like apply it from left to right, but this is the convention. Maybe it was like invented by Chinese or Arabs who like read from right to left. But this is the standard, so get on with it, get used to it, because that's what everybody's using. The same thing is like when you'll be doing graphics, OpenGL, also like composing transformations. You have to read it right to left. The transformation that's applied first is the one on the right. The one that's applied second is the one to the left. So really read it this way. I guess if you are Chinese, it's more natural for you that way. Is that? I don't know. Is there anybody Chinese? Or so is it true that you read from right to left? Okay. So but some languages do. Hebrew. I thought of Arabic or something.
Arabic is the same.
Oh, so not Chinese. Okay. Well, when it comes to composing transformation, everybody's going to be reading from right to left. That's the convention. Okay, so I know that linear transformations can be represented by a matrix, right? And I described the matrix vector multiplication, so we have like a nice, elegant way of denoting it. So if I have some transformation, some matrix B and some vector V, then the result of applying the linear transformation is equivalent to the result of matrix vector multiplication B times B, right? So this is my matrix, this is my vector. Now I can think, what if I have another transformation now, transformation A, that I apply to the result, right? So this is one matrix, this is another matrix, and the dimensions all have to agree, otherwise this would not be defined. But because of what we have shown here is that the composition of linear transformations is a linear transformation, this means that there has to be some other matrix C which gives me exactly the result, right? Like when I was talking about the algebra, like your hand should be like shaking to like do something like this, to write like this, right? To be able to apply associativity. Now the problem is that we don't really know what this really means, because a composition of two matrices we didn't discuss yet, so I'm gonna discuss it right now. That's matrix multiplication. So the point is that I can define the matrix C as matrix multiplication of A and B, so that this is true, so that the C is the matrix corresponding to the composition of the matrices corresponding to linear transformations A and B. So another absolutely crucial thing in linear algebra is matrix multiplication. And I guess I was going through all this like linear transformation business and the vector spaces and so on to basically justify this, right? Like if I just throw at you a definition of matrix multiplication, it might like look arbitrary. So let's look at it first. So if I have two matrices, one matrix is A and it has L rows and M columns. And B is another matrix which has M rows and N columns. Then I can define a product of the two matrices A and B. The matrices which corresponds to the matrix which is the product is C. That's the matrix I'm defining now. And I will say that this will be a matrix of dimension L times N. So notice this. A was L times M, B was M times N, and the product is L times N. I think I will again draw an image to give you like a graphical representation of what it means. And here is how I compute the elements of the matrix. So I can uniquely, easily compute them from the elements of A and B. So I know the matrices A and B, I know their dimensions, I know their elements. And I do this summation over K. Notice that the K is like close together. And this is how I get my matrix multiplication. So the way I explained it now, you will be like, why would you want to define it this way, right? Like, why wouldn't you want to define it some other way? For example, if I had like square matrices, two square matrices, why I wouldn't want to multiply the corresponding elements and then sum of the whole thing together? Wouldn't that be like a better matrix multiplication? You could be wondering this, right? The point of this matrix multiplication is that this is the algebraic counterpart of composing linear transformations. So if I have my linear transformations represented by matrices A and B, then the linear transformation represented by matrix C is exactly the linear transformation that corresponds to composition of A and B. And that's why it is defined this way. If you were curious, you can actually derive this. You don't have to like trust me on that definition or like accept the definition, but like basically write out what it means from the definition B times V, and then again apply the same definition. So this is still a vector. Wait, this is a different paper. I'm not confusing here. Where did I put it? Ah, there I put it. That's the previous slide. So the B times V is again a vector, right? So I can multiply it with a matrix. So this way I can basically derive what the elements in C could be. So if you're like really into math, this is like an exercise you can try. Basically derive this from matrix vector multiplication by applying the matrix vector multiplication twice. This is what you should get. You can do that for like your own homework if you are interested. Not everybody has to do that. So I promised you a picture, right? Let's look at a picture. So let's see. So let's say that my A matrix is like this. I prepared some picture. Yep. So this is my A matrix. So the number of rows here is L. The number of columns is M. And I have a B matrix, and I have to be careful because the number of rows of B have to be the same as number of columns of A. So like the length of this side I want to be the same like this, so just to give you the right picture there. Now this side now can be arbitrary, so I can like make it big, for example. So this is my matrix B. So now so this is M. The number of rows of B is M. The number of columns of B is N. And the result of the product is going to be a matrix L times n. So here it will be small, and here it will be the big one. So this is my matrix C, or the product A, B. And now we can also, like, as I was giving you like a graphical interpretation of matrix vector product, there's a very similar interpretation of matrix product. Probably the simplest way to look at it is by considering the columns of B. So if I denote this vector as C1, C2, like column, maybe that's not the best notation because then it looks like elements of C. So let's say D, D1, D2, and so on to D what? Dn, right? Yeah, it has n columns. So those are the column vectors. So what the matrix product is actually is nothing but the matrix vector product applied to all of the columns individually. So the first column of the product, let's denote it now C. This is just the matrix vector product A D1, right? So let me write it here. So C1 is just A D1. The matrix vector product I just defined on the previous slide. Then the C2, well, guess what's going to be? It's D2 times n, right? And so on. Up to my Cn. So that's what's written here. It's the matrix formed by applying A to all of the columns of B, my vectors D1, D2, and so on to Dn. So this is also like how you can remember the. You don't remember. Try to remember this formula. Even though one interesting thing you can remember is that there are these two indices I and j, and they are like on the outside, and the k I'm summing over is on the inside. If you have been studying physics, then you know that there is this Einstein convention, summation convention, which says that this is just okay, that can just leave out the sums, because the k is not on the left hand side. So if it's not appearing there, this would be like a syntax error. So you imply there is a summation. The summation is like silent there. I guess like there is like a silent multiplication, right? So you just like assume it's there. But like this is just sometimes used in physics. I don't like this notation very much. But the point is that this index I was summing over is like the one inside. Okay, so now we know what is matrix vector multiplication and matrix multiplication. So the matrices are cool. Matrices also form an algebraic structure. Just like vectors form a vector space, I can think about the set of all matrices, and now there are some nice properties. So the obvious things I can do to a matrix, the same I can do to a vector, right? I can obviously multiply by a scalar. Any questions? Anything? No? So multiplying matrix by a scalar is trivial. I just multiply every element of the matrix by the scalar, right? No big deal. If I have two matrices of the same size, so I have one matrix m by n, another matrix m by n, I can sum them together by summing all the components individually, right? If I have matrices of different dimensions, I cannot sum them. It's not defined. But that's not it, right? Like so far, this would be like nothing but just another vector space, right? The cool thing about matrices is that now I have a well-defined multiplication. So this gives me a little bit more powerful algebraic structure, because I can not just add things together and multiply by a scalar, but I can also multiply two matrices together. That's something I could not do with vectors. The best thing I could do was like a vector, like a dot product, right? But dot product is fundamentally different. Dot product takes two vectors and returns a scalar, right? With matrices, I have one matrix, m by n, and n by l, and the matrix product returns a matrix. Different dimensions, but if the matrices were square, if I had matrices n by n, then multiplying two n by n matrices gives me, of course, n by n matrix. So that means that, and we will talk about that more, that this leads to group theory. Because once I have multiplication in the algebra, then I can do much more with it. Essentially, it becomes a more powerful algebra. It also means that we need to be more careful what we are doing here, because let's look at the properties of matrix multiplication. So this is algebra. So we have to do some more what I consider the boring algebra. So if I have three matrices, and they have to have the right dimensions, and two scalars, then all of these statements are true. So the first statement is associativity. So it doesn't matter if I first multiply b and c, and then multiply the result with a, or if I first multiply a and b, and then the result multiply with c. Again, this is only defined if the dimensions match, right? Yeah, sorry about that. So the number of columns of A has to be the same as number of rows of A, and the number of columns of B has to be the same as the number of rows of C, so that the multiplication is defined. So if they are all square, it's all fine, right? That's simple. So matrix addition, and so actually no, let me comment on the associativity. This would be actually another nice homework if you are not. If you still have time after doing the homework you have to do, the MATLAB 1, you can like take a piece of paper and try to prove this by definition of matrix multiplication, right? You look, what is the element ij here, what is the element ij here, and you should get that they are equal. So to prove the commutativity that a plus b is the same as b plus a, that's trivial, right? That's the same like commutativity of vector addition, right? Just because I'm just adding all the components doesn't matter if I do x plus y or y plus x, if x and y are real numbers. Same way for the scalar multiplication distributivity. So obviously, doesn't matter if I first sum the matrices and then hit them by a scalar, or if I first do the scale multiplication and then sum the results together. What is slightly more interesting is the distributivity property. And here we actually need to do it from both sides. So we will need to differentiate between matrix multiplication from the left and from the right. I will get to it on the very next slide, why we need to do that. And this is just saying that the matrix product here, so this is again a matrix product of A and B plus C. B plus C is another matrix, and I do matrix multiplication with A. And this says it's the same as if I do matrix multiplication AB and add it with minimum AC, of course. I guess, I hope I'm not boring you. This algebra can get a little boring. It doesn't even matter if you put scalars inside it. Quite obviously. The catch here is, and this is not boring, this is important. I mean, even the boring things are important. Matrix multiplication in general is not commutative. You might think, yeah, that's obvious. If I have rectangular matrices, then the B and A might not even be defined, right? If A is m by n and B is n by l, then I clearly cannot do B times L, because this would be n times L times m times n. So it's not even, doesn't even make sense, right? For square matrices, if both of them were n by n and n by n, then I could switch it and would be defined. The problem is I would get different numbers. So I would not get the same result. I could compute it, but I'd get something different. It doesn't always, not every two matrices must be not commutative, right? Like if I take the identity matrix You know what is the identity matrix? That's the matrix that looks like this. Zeros. And so on. 1. So the identity matrix is a square matrix and has 1s on the diagonal and 0s everywhere else. I've probably seen this in MATLAB, right? Or if you haven't, that's like one of the basic matrices. That's basically the matrix that plays the role of like. No. I take this back. What I wanted to say is that the matrix, the identity actually commutes with any matrix, right? Because if I multiply the identity with any matrix, I just get the matrix back. The identity does nothing to it, as you can see. So in this case, it does commute. So AI is IA. The point is that this is not true in general. I can find two matrices, even if they are square, where I have a different result for AB and for BA. I just get different numbers. There's a geometric meaning to it, but I think we will get to that later. At this point, it would probably be more confusing than not. So now remember that matrix multiplication is not commutative. So let's do one example, slightly more interesting example. Like to all what all can we apply this theory of matrices and vector spaces. So I told you already before that like we can define a vector space on functions, right? So let's think about a special subset of functions, polynomials of degree less than or equal than 2. So those are functions with this form. So those are functions that map from the real line to the real line, right? I give it a real number, I get a real number back. And they are parameterized by these coefficients A, B, and C, right? You probably know what are polynomials, and this is the degree 2. If A is 0, it has degree less than 2. So the set of all these polynomials, I can also be looking at them like as the graphs of function, right? They are just not like from 0 to 1, that's what I was drawing previously, but they are defined on the entire real line. This would not really be a degree 2 polynomial, more something like this would be like a degree 2 polynomial. But I was just saying you can visualize it as some functions, some lines basically. So for this intuition, it's trivial that this forms a vector space. The set of all polynomials of degree less than or equal to is a vector space because I can define scalar multiplication and vector addition, right? That's what I was talking about this the last time. Now what is interesting is that it's easy to find a basis. So I can define these three functions, these three polynomials, x squared, x, and 1. And any polynomial of degree less than or equal to, I can express as their linear combination, right? That's what I wanted from a basis. So this is what these three guys, f1, f2, and f3, are a basis of this space. Because if I take any polynomial like this, I just need to do a linear combination of these guys, f1, f2, and f3, and I get it back. And these A, B, and C are coordinates of that polynomial, or my vector, right? Here, these I could also call them vectors. Now I defined a vector space. And those are the coordinates of the vector with respect to the spaces. Now let's take another vector space. So could you tell me what is the dimension of this vector space? From your intuitive understanding of dimension? 3, yeah. So fairly safe bet, right? I can vary 3 degrees of freedom. So let's take another, so this will be like my V1. Let's look at another one, another vector space, which will be my V2, because I want to give you an example of linear transformation. So I'm like setting up some interesting vector spaces. So the second one is similar. I just take all polynomials with degree less than or equal to 1. So really just this, bx plus c, where b and c are variables, are my parameters. So the same thing, I can do the same thing. I can define a basis. Let's call them now g1 and g2. And again, any polynomial of degree less than or equal 1, I can write as a linear combination, of course, of these two basis vectors. And the B and C are the coordinates of the vector with respect to the basis. So now I have defined these two vector spaces, which are function spaces, really. They're finite dimensional function spaces. I can give you a sort of interesting example of a linear transformation, differentiation. So the space of polynomials is a space of functions, and I can differentiate them, right? And differentiation is a linear transformation. You may know this from calculus. If you don't, then you just have to trust me, because this follows from the properties of differentiation. So if you haven't had calculus, then you just have to believe me that if I differentiate the sum and scalar multiplication of functions is the same as I first differentiate the functions. So the f prime and g prime means the derivatives of the functions. And the alpha and beta is just scalar multiplication and addition. So, and remember, now the point. It's about time for a point, right? As I said before, the linear transformation is completely explained by saying what does it do on the basis, right? So all I need to do to capture the differentiation, being a linear transformation, example of a linear transformation, I need to say what does it do on the basis vectors of on my f1, f2, and f3. Remember, what was f1 was x squared, f2 was x, and f3 was 1, right? So if I differentiate f1, I get 2x. If I differentiate f2, I get 1. And if I differentiate f3, I get 0, right? So this is what is written here. This gives me 2x. This is differentiating the first one. This d means the differentiation operation. It's a linear transformation between these two vector spaces, which happen to be function spaces. And that means that I can describe the differentiation using a matrix, which I think is cool. It's sort of obvious if you think about it, but and this is what the matrix is. So if my first polynomial has coefficients a, b, and c, meaning it's a x squared plus bx plus c, then differentiation gives me a polynomial 2ax plus b, and nothing for c, and that's exactly what this matrix vector product does. So I guess the intellectual development, you might be like first in the face, oh, that's amazing. So differentiation of polynomials, not of other functions, right? Is a linear transformation. Or you might be like, oh, that's boring. So that's like the two facets of mathematics. Either it's like super cool or boring. So once you understood it, it's boring. Before you understood it, it's super cool. And I think this is a good place to stop for now, because the time is also up, unless you have, of course, some questions. So if you came late, or don't forget, there's the homework due on Friday. It's just like some MATLAB, basic MATLAB programming to get you started, and we will do some more interesting MATLAB project. So unless you have some more questions, then have a good weekend, and I'll see you on Monday.